We'll start in 2 minutes. Okay, we'll start now. Good afternoon, everyone. So, this is a problem solving session for the NPTEL course, Fluid and Particle Mechanics, and the course code is NOC 25CH49. So, as we all know, this is the last problem solving session. Since it is a 12 weeks course, we have almost covered 11 weeks, and this is our last session. So, just to recollect, the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And the live sessions are handled by myself, Ankara Karthika. I'm a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, the sessions have been happening every Saturday from 3 p.m. to 5 p.m. and today will be the last sessions. So similar to previous classes, we will be solving problems related to that particular week's assignment, and we'll start now. So course layout. So as we all know, this is 12 weeks course. So in the 12 weeks course, what we have seen is introduction to Navier-Stokes equation, exact solution, Taylor-Quick flow, dimensional analysis, turbulent flow, friction losses, Moody's chart, and boundary layer theory. So boundary layer theory is for week 12. But apart from that, we have seen covered almost everything else. And when we talk about particle mechanics, we have covered on introduction to particles, their characterization, particulate phenomena, Brownian motion and forces, motion of particles in a fluid, terminal velocity, particle separation, and sedimentation of dilute, concentrated, and flocculated dispersions, and packed and fluidized bed. And week 12, it was about filtration. So for the books and references, although we have seen, but just to quick recollection. So first one is Unit Operations of Chemical Engineering by Warren Lee McCabe, Julian Cleveland Smith, Peter Harriet. This is the book which we have been using mostly for fluid mechanics at our bachelor's level, and second one is fluid mechanics by Frank M. White, and third, introduction to particle technology by Martin J. Rhodes, John Wiley and Sons. So for few references, we have Coulson and Richardson's Chemical Engineering, John Metcalf Coulson, John Francis Richardson, Butterworth Heinemann 1999, Fluid Mechanics by Piyush K. Kundu, Elsevier 2013, and Principles of Colloid and Surface Chemistry by Paul C. Hemans and R. Rajagopalan, CRC Press 1997. And last one is Transport Phenomena by Bert Stewart Lightfoot, Wiley and Sons 2002. So for week 12, what we are going to see is like boundary layer theory, momentum integral analysis, boundary layer, and again continuation to that, and boundary layer differential approach, and laminar and turbulent boundary layer. So for week 12, the course is on the boundary layer. So the behind the theory about boundary layer would have been the videos provided by the professors. So I hope you all have seen that. So now we'll start with the problems. So question 1, what we have is, okay. For flow of sea level standard air, density is 1.2 kg per meter cube and kinematic viscosity is 1.5 into 10 power minus 5 meter square per second at 3 meter per second parallel to a flat plate. The boundary layer thickness at a distance of 45 centimeter from the leading edge is dash centimeter. So I repeat the question. For flow of sea level standard air and its density is 1.2 kg per meter cube and kinematic viscosity is 1.5 into 10 power minus 5 meter square per second, and it is viscosity basically is 1.8 into 10 power minus 5 kg per meter second, and it is traveling at parallel to a flat plate and its velocity is 3 meter per second. So what is asked? We need to find what is the boundary layer thickness at a distance of 45 centimeter from the leading edge is dash, and answer is expected in centimeters. So we'll see how to solve that. So before that, to tell about what is boundary layer, it is a thin region near the surface where a fluid's motion is slightly affected by the surface presence and fluid's viscosity. So because of that, there will be a generation of velocity gradient, and which has like 0 at the surface to free stream velocity away from the surface of it. So this is like a concept used mostly in the fluid mechanics to analyze the fluid flows, so, by simplifying it. So now we have to find at what distance from the, I mean at 45 centimeter from the leading edge, what will be the thickness. So it is, first let us see what is given. So what is given is, leading edge distance is given as 45 centimeter or it is 0.45 meters, and velocity is 3 meter per second, and kinematic viscosity is 1.5 into 10 power minus 5 meter square per second, and density is 1.2 kg per meter cube, and its formula is actually delta is equal to 5x by root of Reynolds number x. So what we need to now calculate, now we need Reynolds number. Reynolds number is equal to rho Vx by mu, and rho is density and mu is viscosity. So what are we given? We are given with kinematic viscosity, so which is nothing but mu by rho. So it is Vx by nu. This is nu, this is nu. So Vx by nu, and nu is kinematic viscosity. If you remember units itself, we can write it clearly. Mu is kg by meter second and density is kg by meter cube. So this becomes meter square by second. So this is the kinematic viscosity unit, and mu is this unit is kg by meter second, and this is rho, kg by meter cube. So mu by rho gives us nu. So Reynolds number is equal to rho v x by mu, or we can write it as mu by rho. So kinematic viscosity comes in the denominator. It becomes Vx by nu. So V is now 3 meter per second and X is given as 45 centimeter or 0.45 meter divided by 1.5 into 10 power minus 5. So it becomes 10 power 5. So it is 90,000. So Reynolds number is 90,000 at this. Once again. Yeah, Reynolds number is 90,000 here. So what we need to see is now delta. So delta is again 5x by Rex. So 5 into 0.45 divided by 90,000. So it becomes 2.5 into, root of 90,000, sorry. 5 into Rex, 5 into x divided by square root of Rex. So Reynolds number is 90,000. So it becomes 7.5 into 10 power minus 3 meter. But in the question, if you remember, it was asked in centimeters. So it is in centimeters, it is 0.75 centimeter. So the thickness at the distance of 45 centimeter from the leading edge is 0.75 centimeter. So that's how we do this. Now moving to next question, it is the wall shear at a distance of 45 centimeter from the leading edge is dash Pascal. The wall shear stress at a distance of 45 centimeter from the leading edge is dash Pascal. So now we have to calculate the wall shear stress at 45 centimeter distance only. So for that, what are we going to do? We are going to just check the formula once. Because now it is tau w. So tau w is half into rho u square into Cf. Cf here is the skin friction coefficient. So it varies depending on the flow regime, whether laminar or turbulent. But here for a flat plate, we can take it as less than 5 into 10 power 5 as laminar. So here it is 90,000. So we can take it as a laminar. And so now we have to find Cf first. So tau w is equal to 0.5 into rho u square Cf. And here Cf is the skin friction coefficient, and Cf depends on Reynolds number, whether it is a laminar flow or it is a turbulent flow. So to get here the flow is in a flat plate. So we can consider that if it is less than 5 to 10 power 5, it is a laminar flow. So on that basis, since we got it as 90,000 as the laminar flow, so we can take the formula for laminar flow. So Cf is equal to 0.664 divided by square root of Rex. So again we have to calculate Cf. So it is 90,000 square root, and that gives us 300. Oh, so 0.664 divided by 300, it is 2.213 into 10 power minus 3. That is a Cf. So now since we know Cf, we can substitute it in the wall shear stress formula. And if we substitute there, what will we get? 0.5 into rho. Rho is 1.2. Okay, we'll go there. 0.5 into 1.2 into, u square. U is 3 here, 3 meter per second. So we are substituting 3 into CF is 2.213 into 10 power minus 3. So we are substituting everything here. So our final answer is 3 square into 2.213 into 10 power minus 3. So answer is 0.011952 Pascal. So wall shear stress is 0.0191 Pascal aroundly. I mean by taking a round off. So now we will go to question 3. Okay, so here Karman's momentum integral estimate is equally true for turbulent boundary layers as for as for the laminar boundary layers. But the analysis will fail if the plate is rough. So we are given one statement. So we are what is given? Karman's momentum integral estimate is equally true for turbulent boundary layers as for the laminar boundary layers, but the analysis will fail if the plate is rough. So we are asked to say whether it is true or false. So answer is actually false. We'll see why. Okay, while Karman's momentum integral equation is valid for both laminar and turbulent boundary layers, the analysis does not inherently fail for rough plates. It requires modification to include the roughness effects. The presence of roughness alters velocity profiles and friction coefficients, requiring additional modeling. Okay. So what is mentioned here is, like in the question what is asked, Karman's momentum integral estimate is equally true for turbulent boundary layers as for the laminar boundary layers, but the analysis will fail if the plate is rough. So in the question it is given that Karman's Karman's momentum integral estimate is true for both turbulent boundary layers and laminar boundary layers, but it is given that it will fail for rough plates. So we are asked to find whether it is true or false, and the answer is false. Why? Because Karman's momentum integral equation is valid for the laminar flow systems and boundary layer laminar and turbulent boundary layers, and if the plate is rough it does not inherently fail. Rather we require some modifications to include the roughness effects. If the roughness is producing such flow variation, we need to modify the equation, and because of that the presence of roughness will alter the velocity profile and the friction coefficients. So we need additional modeling, but that doesn't mean that the analysis will fail for the rough plates. We need to model it by including the roughness effects. It doesn't mean that the analysis will fail. So that is for question 3. Now moving on to question 4, what we have, laminar boundary layers separate faster than turbulent boundary layers, though turbulent boundary layers are thinner than laminar boundary layers. So what is given is, again it is a true or false question. Option A true, option B false. So laminar boundary layers separate faster than the turbulent boundary layers, even though the turbulent boundary layers are thinner than laminar boundary layers. So answer is actually true. We'll check first. Yeah, answer is true because laminar boundary layers separate more easily due to the lower momentum transfer and less energy near the wall to overcome the adverse pressure gradients. Although turbulent boundary layers tend to be oh they have due to mixing they have higher momentum near the wall, allowing them to resist separation longer. So they separate. um, okay. So basically, answer is true, but laminar boundary layers separate faster than the turbulent boundary layers, and turbulent boundary layers resist the separation for a long time than compared to the laminar boundary layers, because uh, laminar boundary layers have less momentum near the surface, and turbulent flows due to the chaotic mixing and transports high energy fluid from the free stream closer to the wall, so they get the momentum to resist the adverse pressure gradient and stay attached longer. So laminar boundary layer actually, yeah. Due to the low momentum transfer and less energy near the wall to overcome the pressure gradient, so they separate faster. So, whereas in turbulent boundary layer, they have the chaotic mixing and transport higher energy fluid from the free stream close to the wall, so it gives the momentum to resist the adverse pressure gradients and they stay attached for the longer time. So when we compare the laminar boundary layer and the turbulent boundary layer, laminar boundary layer consists of like smooth parallel layers with low velocity near the surface, and like this makes low momentum, and it makes it um, like the fluid actually like separates from the surface more quickly uh, when it is encountering the adverse pressure gradient, whereas in turbulent boundary layers that will resist the adverse boundary gradients for a longer time, because uh, they transport the higher energy fluid from the outer part of the boundary layer and all. So this added energy will give the fluid more momentum and allow it to withstand the stronger pressure gradient before it separates. So it resists the separation for a longer time, therefore making the separation slower process. So that is for question 5, sorry, question 4. Now moving on to question 5, what we have here is, okay. For flow of sea level standard air and whose density is 1.2 kg by meter cube, and oh, kinematic viscosity is 1.8 into 10 power minus 5 meter square per second at 36 meter per second parallel to a flat plate. The Reynolds number at a distance of 20 centimeter from the leading edge is dash. This is similar to the first problem which we saw. So what is asked? We are given the density, and density is, I'll just check the value once. It is not actually kinematic viscosity. It is a dynamic viscosity, 1.8 into 10 power minus 5 by kg by meter second. So I'll read the question again. For flow of sea level standard air, and air has density of 1.2 kg by meter cube and viscosity of 1.8 into 10 power minus 5 kg by meter second, at flowing at 36 meter per second parallel to a flat plate. Reynolds number at a distance of 20 centimeter from the leading edge is dash. So we are asked to find the Reynolds number. So Reynolds number, it's like a straightforward problem only, so we'll be able to get it. So for that, first what are we going to do? We'll write the given first. What is given? The distance from the leading edge is given as 20 centimeter, and velocity is given as 36 meter per second, and Viscosity was given as 1.5 into 10 power minus 5 kg by meter second. Actually, symbol, insert, close, equal to 1.8 into 10 power minus 5 kg by meter second. This is what is given explicitly. For our understanding and ease of solving, we have taken it other way. Because in most problems nu was given, that's why I know, like I mentioned about converting from mu to nu. So nu is mu by rho, and therefore it is 1.8 into 10 power minus 5 by it also need to be written, right? Equal to 1.2 kg by meter cube. So nu is equal to mu by rho. So now we are given a distance from the leading edge as 20 centimeter or 0.2 meters, and velocity is given as 36 meter per second, and mu is 1.8 into 10 power minus 5 kg per meter second, and rho is 1.2 kg by meter cube. With the information provided on air density and viscosity, we can calculate its kinematic viscosity, and that is mu is equal to mu by rho, where mu is 1.8 into 10 power minus 5 divided by rho, that is 1.2. So it is 1.5 into 10 power minus 5 meter square per second. So if we do it with 6 itself, it is like 6.2 into 0.3 divided by 0.2, or 3 by 2, it is 1.5. So directly itself we can do. So now what we need to find? We need to find the Reynolds number. So what is the formula? Re is equal to rho Vx by mu, or it is Vx by nu. So here just V is V and this is nu. Nu is kinematic viscosity and it is mu by rho. So what is the solution? Like we have to substitute every values in the formula, and what we will get, V is 36, X is 0.2, 36 into 0.2 divided by nu. Nu is 1.5 into 10 power 5. I mean divided by 10 power minus 5, so it becomes 10 power 5 in the numerator. So what happens? We will get 4,80,000. So the Reynolds number is therefore 4,80,000. So that is the question 5 solution. It was simply asked to estimate the Reynolds number, and we did that. Moving on to question 6, what we have is the boundary layer thickness at a distance 20 centimeter from the leading edge is dash centimeter. So now we are asked to find the boundary layer thickness at a distance of 20 centimeter from the leading edge. So what we have to do, we have to calculate it similar to the second or first problem which we did. So here what is asked? Boundary layer thickness is asked. So boundary layer thickness is delta equal to 5x by square root of Reynolds number. So we will directly go there. So x is given as 20 centimeter, and Rex we calculated from the previous problem. Rex is rho Vx by mu, and we calculated it as 4,80,000 in the previous problem, and formula is so delta equal to 5x by square root of Rex. So x is 0.2 and Reynolds number is 4,80,000. If we take square root, x is zero point 0.2. So that gives us 1.44 into 10 power minus 3, or it is like in centimeter it is 0.144 centimeters. So what we did, we are just substituting everything here. So delta is equal to pi x by square root of rex. So x is zero point 0.2 and rex is 4,80,000. We are just substituting here. So 5 into zero point 0.2 divided by square root of 4,80,000, which is nothing but 1.44 into 10 power minus 3 meter. But if you remember, in the question it was asked to calculate in centimeters. So it becomes into 100. So mm, uh, it becomes like 1.44 into 10 power minus 1 centimeter, or it is 0.144 centimeters. So that is how we do the question 6. So question 6 is also a straightforward problem. Now we'll go to next question. The wall shear stress at a distance of 45 centimeters from the leading edge is dash Pascal. So yeah, similar to how we do in the previous problem, we are going to do. But what exactly is like wall shear stress? Wall shear stress is actually the frictional force acting per unit area uh, from uh, from the fluid on the solid surface. So it is calculated in the boundary layer theory as the viscous shear stress at the wall using tau is equal to mu into u by y at y equal to 0. So it is arising from the velocity gradient between the stationary wall and the moving fluid. Like, what is the gradient? So between the fluid and the wall. So, and this is causing for the this is one of the source for the skin friction drag. So because this is the force exerted by the fluid on the wall per unit area due to the internal friction and friction between the fluid and the surface. So that is why we are calculating this. So how do we get it? Is tau w is equal to, first we'll write the given. So given is density is given as 1.2 kg by meter cube, and u is given as 36 meters per second, and formula, as we all know, it is tau w is equal to zero point 0.5 into rho into u square into cf. So as I mentioned, cf is the skin friction drag. So skin friction coefficient. So it is CF we need to calculate, and CF again depends on the whether the flow is laminar or turbulent. So CF is equal to 0.664 divided by square root of REX, and REX here we have calculated earlier itself, it is 4,80,000. So it is CF is equal to 0.664 divided by 4,80,000 squares. I mean square root of 4,80,000. So if we do that, first we'll find CF. Here it is 4,80,000, even though it is large number, it is less than 5 into 10 power 5. So we are taking it. So, square root of 4,80,000 is 692.82, and 0.664 divided by 692.82 gives us 9.58 into 10 power minus 4. So this CF we have found, and we have to substitute the skin friction coefficient back in the formula. So it becomes 0.5 into rho is 1.2 into u square. U is, okay, I'll show that, 0.5 into 1.2 into 36 square into 9.58 into 10 power minus 4. So this is rho, sorry, 0.5 into rho into u square into CF. CF we have calculated, so we are substituting that, and 336 square into this. So it is 0.7449 Pascal. So it is like shear stress, right? So it is Newton by meter square, force per unit area. So it is in Pascal unit. So what was there any unit particular asked? Yeah, in the question it was asked to calculate the shear stress, wall shear stress at a distance of 45 centimeter. Oh, okay. Did we calculate it at a 45? Yeah, it is not actually 45 centimeter, it is actually 20 centimeter. If it is 45 centimeter, again we have to do the calculation. So it is like Reynolds number will vary for 45 centimeter. So answer is actually, I mean in the question it was 20 centimeter. I forgot to change, like as I mentioned earlier also, like I have been changing the numbers in the question. So due to some mismatch, I forgot to change in this particular question. But question is, what is the wall shear stress acting at a distance of 20 centimeter from the leading edge? So that's why we are using the same Reynolds number and we are calculating the solution. So that is for question 7. We'll go to question 8. Identify the right statements. So now we are given few statements. We have to identify which one of them are right. For a uniform flow past a flat plate, the boundary layer exists because the flow has to respect the no slip boundary condition on the surface of the plate. The momentum thickness in Carman's analysis of flat plate is defined as theta is equal to delta, integral of u by u 1 minus u by u the whole square into dy, integral from 0 to delta. The drag force acting on the plate is related to the momentum thickness theta as dx is proportional to 1 by theta, and the local Reynolds number of a boundary layer does not change with distance from the leading edge. None of the above. So answer is actually option A. So it is we have to identify the right statement. So the right one is, for uniform flow past a flat plate, the boundary layer exists because the flow has to respect the no slip boundary condition on the surface of the plate. So as we mentioned, it is like the separation between the fluid flow and the solid surface. So we mostly go with the no slip boundary condition on the surface of the plate. So because of all these factors only, we have the boundary layer existing. So answer, I mean this option A is the right answer. So what are the wrong things in the other statements? So let us find out now. So this is the option number. So now we are going to see why it is true and why it is not true. So first one is that is true. Boundary layers are formed because the fluid velocity at the wall must be zero due to the no slip boundary condition, and creating a region where viscous effects are important. So that's why we study about boundary layers, right? So next one is the momentum thickness in the Carman's analysis of flat plate is defined as theta is equal to 0 to delta u by u 1 minus u by u of dy. The question it was given as 1 minus u by u the whole square, but it is not square. In the momentum thickness in the carbon's analysis of flat plate, it is defined as theta is equal to integral of u by u times of 1 minus u by u, and integration is from 0 to delta, and it is integrating with dy. So that is the issue with the second statement. And third statement, drag force is directly proportional to the momentum thickness, it is not inversely proportional, so C was also wrong. And finally, what is wrong with question D is the local Reynolds number increases with distance from the leading edge. So it is basically rho v x by mu. So obviously it is depending on the distance from the leading edge. So those are all the four statements. So now we'll go and read the question once again. Now it will make sense. For the uniform flow past a flat plate, the boundary layer exists because the flow has to respect the no slip boundary condition on the surface of the plate. So this is a true statement. Second statement, what is given? The momentum thickness in Kalman's analysis of flat plate is defined as theta is equal to integral of u by u into 1 minus u by u the whole square dy. Integral is from 0 to delta. What is wrong here? Square should not come. So that is the false factor in the statement. Third one, the drag force on the plate is related to the momentum thickness d theta, as d is inversely proportional to theta, that is d is proportional to 1 by theta. So this is wrong because ideally d is proportional to theta, so that is the wrong uh, factor in option C, statement C. And last statement, the local Reynolds number of a boundary layer does not change with the leading distance from the with the distance from the leading edge, whereas it is false, it increases with distance from the leading edge. So option A is the right one. B, C, D are having some issues with them, which we have seen why in the next slide as well. So that is for question 8. Now let us go to question 9. Now we have to identify what is the wrong statement. So first statement, it is given that the skin friction coefficient in a flat plate boundary layer calculation is analogous to the friction factor F in flow through ducts. Second one, displacement thickness is always equal to the boundary layer thickness. Option C, boundary layer can either be laminar or turbulent. Option D, the ratio of displacement thickness to the boundary layer varies only with the dimensional velocity profile u by u. Option E, none of the above. So what is asked is, we are asked to identify the false statements. So if we read the statements itself, we will understand which is wrong actually. First one is actually skin friction coefficient in a flat plate boundary layer calculation is analogous to the friction factor F in flow through ducts. So this is a true statement. Answer is option B. Let me just check. Yeah. Second statement is a displacement thickness is equal to the boundary layer thickness. It is always equal to boundary layer thickness. It is given like that, but it is false. We'll see problems also where in the coming up slides where displacement thickness is different from the boundary layer thickness. So option C is boundary layer can either be laminar or turbulent. It is again depending on the flow Reynolds number. And finally, it is ratio of displacement thickness to the boundary layer thickness varies only with the dimensional velocity profile u by u. So delta and delta star like varies only with the dimensional velocity profile u by u. So this is also true. So second statement is the only false statement. So we'll see why, I mean, what is the wrong one there. Displacement thickness is always less than the, oh, okay, actually I shouldn't put it like this, it is a bit confusing. The false statement is statement B. False statement is statement B. Displacement thickness is always less than the boundary layer thickness and depends on the velocity profile within the boundary layer, which we have seen it in the option statement D actually. The other statements are true. Skin friction coefficient is analogous to friction factor index. And boundary layer can be either laminar or turbulent. And ratio of displacement thickness to the boundary layer thickness depends only on the dimensionless velocity profile u by u. So this is also true statement. So second statement is actually contradicting with statement D. From that itself we can identify one of them as wrong. Because in 4 it is ratio of displacement thickness to the boundary layer thickness depends on the dimensionless profile u by u, whereas in the B statement it was given that both are same. So B is actually wrong because it is always less than the boundary layer thickness and depends on the velocity profile within the boundary layer. And we'll see like a few we'll be seeing few problems on displacement thickness as well in the one of the problems I remember. So yeah, we'll see that. Yeah, that is for question 9. Now, now we'll go to question 10. Okay, we have a flow through a square duct which is having a flow velocity of 3 meter per second and the distance is 2 meters and the duct is 30 cross 30 centimeter square duct. So what is given is air at 20 degrees Celsius and 1 atmosphere and air density is 1.2 kg by meter cube and viscosity is 1.8 into 10 power minus 5 pascal second, enters the 30 centimeter square duct as shown in figure 1. We can put 30 centimeter cross 30 centimeter square duct as shown in figure 1. This is figure 1. What is asked? Using the concept of displacement thickness, estimate the Reynolds number at a position x is equal to 1 meter away from the entrance. So what is asked? Using the concept of displacement thickness, we have to estimate the Reynolds number at a position x is equal to 1 meter away from the entrance. So we'll see how to solve that. What is given? It is not P. It is rho. That is density. Is 1.2 kg by meter cube. X is equal to 1.1 meter. Mu is 1.8 into 10 power minus 5 kg by meter second. Was it given like that? Yeah, it is Pascal second. Whatever. It is Pascal second. And V is flow velocity is 3 meter per second. I think I should write it better. Because symbols are kind of confusing, I guess. The Reynolds number is equal to rho v x by mu. So Reynolds number is equal to rho v x by mu here, so we know everything. Rho is 1.2 kg by meter cube, v is 3 meter per second, and x is 1 meter divided by mu is 1.8 into 10 power minus 5 Pascal second. So it is 1.2 divided by into 3 divided by 1.8 into 10 power 5. So it is 2 lakhs actually. Reynolds number is 2 lakhs. In the question we are asked to find the Reynolds number. So we actually calculated the Reynolds number as 2 lakhs. So I'll just change here, yeah, distance from the leading edge. I mean, I'm just writing what does each symbol represent so that there will be no confusion. Velocity, kinematic. Every time I do that, but this time, yeah, due to shortage of time, I didn't do. Like when you look at it later, you should be able to know what each represents. That's why I'm writing. Density, air, and this is kinematic viscosity of air. And density of, because I'm using different notations everywhere, I just don't want it to be confusing when you are looking at it later. That's why I'm writing. Oh, shear. Just bear with me for 2 minutes. I'll finish it. Coefficient. Yeah. No, I think we are done. Okay. We'll solve question 11 as well, and we'll take a 5 minutes break. The boundary layer thickness at a position of x is equal to 1 meter away from the entrance is dash meters. If you see in the question, it is asked the answer in meters actually. It is not in centimeters. So, or else we can solve the problem and we can do. Yeah. So, boundary layer thickness at a position of x is equal to 1 meter away from the entrance is dash meters. So, it is what is given, x is equal to 1 meter, rex which we calculated in the previous problem as 2 lakhs. So now formula is delta is equal to 5x by square root of rex. So now we will substitute everything. 5 into x is 1 meter divided by square root of 2 lakhs. So square root of 2 lakhs is 447.2, and 5 divided by 447.2, it is 0.011 meters. So boundary layer thickness is 0.011 thickness. If it is in centimeters, it is 1.1 centimeter. But in the question itself, it was asked in meters, so it is not required. So again, if we see distance from the entrance, and this is boundary layer thickness. So yeah, that is for question 11. We'll take a small 5 minutes break. Time is 3:57. We will come back by 4:02 and we'll continue. Like there are 20 problems in total, so we'll continue after taking a break. Thank you. We'll, s- we'll start now. The displacement thickness at position x is equal to 1 meter away from the entrance is dash meters. So what is given? Delta, okay. We need to calculate the displacement thickness at a position of x is equal to 1 meter away from the entrance, and previously we calculated the boundary layer thickness as 0.011 meter. Yeah, I'll better write thickness. So boundary layer thickness is 0.011 meter calculated from the previous problem, and formula is delta star. Delta star is the displacement thickness and it is equal to 0.22 times of delta. And now we have to do the substitution. 1 minute, I'll just check once. Okay, it can be 0.33 or 0.22. I'll confirm the number actually. Delta star is equal to 0.33 times delta or 0.22 times delta. Mm, or 1 minute. I'll check. Yeah, I'll check and I'll update the correct one in the final PPT. But delta star is equal to 0.22 times delta if we take. Uh, it is 0.22 times of 0.011 and that becomes 2.42 into 10 power minus 3. Actually, it is 2.42. That is for question 12. And question 13 is or else just give me a minute, I'll just verify the last problems last problem solution actually. Okay, it is better to go with 0.33 actually. Yeah. It is point. Yeah. In meters is, yeah, 0.00242 meters. So better. Yeah, 1 by 3 times. So we are taking 0.33. Now the total flow rate through the duct is dash through the pipe is dash meter cube per second. So we need to find Q. So we'll see how to calculate that. First, it is duct cross section is given as 30 cross 30 centimeter square. So it is 900 into 10 power minus 4 meter square, or it is 9 into 10 power minus 2, or 0.09 meter square. This is cross sectional area. Yeah. And we are given flow velocity, is it 3 centimeter? It is 3 centimeter. So it is flow rate is Q is equal to U into A. This we have been using for a long time, and U here is 3 and A is 0.09. So 3 into 0.09, it is 0.27 meter cube per second. So that is for question 13. Now we'll go to question 14. Was one problem. Okay, it is here. Okay. In question 14, what is asked is the mean velocity in the core of the flow at a position of x is equal to 1 meter away from the entrance in meter per second is dash. And we'll see how to do that. First, let us write given velocity is 3 meters per second. And what is d? Oh, it is not d actually. Velocity is meter per second. It is 3.3 centimeter. Duct size 30 centimeter. I mean duct length or size is 30 centimeter. Delta star again it is 0.024. It is not 0.024. 0.33 into 0.011. It is 363. 0.00363. So again here it is 363. This is displacement thickness. Again I have a doubt here. Just give me a minute. Just give me 1 minute. I'm just checking that. Just give me 1 minute. Okay, it is delta star only. Okay, I think it is a bit confusing. I'll put X. Okay, delta star is 0.00363 meter, and velocity core is equal to U into duct width by effective width. So duct width is actually 30 centimeter, and effective width is calculated as d minus 2 times of displacement thickness, and effective width is therefore zero point 0.3 minus 2 times of this one 0.00363. So it is 2 into 0.00363 0.3 minus this one, so 0.29274 0.29274 meters, and it is again 3 meter per second into d is 0.3 meters divided by 0.29274. So velocity core therefore becomes 3 into 0.3 divided by this, so it is 3.074 meter per second. I'll repeat once again. So what are we doing? We are asked to find the mean velocity in the core of the flow at a position of x is equal to 1 meter away from the entrance. So what did we do for that? We first got the velocity, and we calculated the duct width, and we didn't calculate, it was given in the question. The duct width and displacement thickness is given as 0.00363 meters, which we calculated from the previous problem. It was question 13, right? Oh, 40, 12. This problem, question 12. So velocity at the core is given as u times d duct width divided by effective width. So effective width is given as d minus 2 times of delta star, and therefore we are calculating the effective width first, and later we are calculating the velocity at the core. So velocity at the core is coming as 3.074 meter per second. So this is how we did the calculation, and now we go to next problem. I hope question 14 is clear enough. So now moving on to question 15, we have a figure actually. We don't require this, I guess. Yeah. We are asked to explain the figure of flow past a sharp plate at a higher Reynolds number. So we have a figure in which fluid is flowing past a sharp plate, and it is at a higher Reynolds number. So Reynolds number is 10 power 7. So there is a small displacement effect, and we have A, B, C, D, E, F, all those things. Small displacement effect is here. So we'll explain what is given in the figure. So first is that this figure illustrates actually the boundary layer development along a flat plate at a higher Reynolds number of 10 power 7. So flow is with uniform flow approaches a thin flat plate. So here what happens is that the plate starts at a leading edge and flow develops along the develops a boundary layer along the upper and the lower surface. So boundary layer so actually the boundary layer is growing in the thickness in the downstream direction. So along the most of the plate, so thickness is actually less than the length of the plate, but the thickness is growing in the downstream direction. So the flow above the boundary layer is only slightly displaced outward, and due to the presence of the boundary layer, so because of the displacement effect, where the effective streamline is actually shifted by the displacement thickness. um, so actually here okay outside the boundary layer, we have fluid velocity remains the free stream velocity, and this is the solid boundary layer. And what else? Okay, we'll see in the question itself. Mm, mm. Okay, so here actually we can see the transition from the laminar boundary layer to the turbulent boundary layer, like laminar boundary layer to the turbulent boundary layer. The transition is also visible. And what else is there? Here it would have attained the free stream velocity by when it reaches here, and here the velocity will be lower than the free stream velocity. And like near the plate we will be feeling the viscous effects, and like away from there we will feel the we won't feel that full of viscous effects. Like near the plate here in the AE and all, the viscous effects will be dominant, and F and all, the viscous effects won't be that dominant. So when we talk about question 15, the figure illustrates the boundary layer development along a flat plate at a higher Reynolds number. So flow setup is uniform flow with velocity u approaching a thin flat plate. The plate starts at the leading edge and the flow develops a boundary layer along both the upper and lower surfaces. The boundary layer grows in thickness in the downstream direction. Boundary layers. The flow above the boundary layer is only slightly displaced outward due to the presence of the boundary layer due to the displacement effect. Well, I'll remove all these things not required. And core region outside the boundary layer, the fluid remains essentially the same as the free stream velocity u, and plate. No, this is not. Okay, like when we talk about key concepts illustrated, The boundary layer flow is nearly inviscid outside the boundary layer, but within the boundary layer, viscous effects and velocity gradients are significant, as I mentioned in the figure itself. The shift or the displacement of the outer potential flow due to the slowing down of the fluid near the wall, the effect is generally small unless the boundary layer is very thick relative to the plate length. Higher Reynolds number, the much smaller boundary layer thickness compared to the plate length is characteristics of higher Reynolds number. Reynolds number, as we have seen, is 10 power 7. So because of that only, like if you remember, boundary layer thickness is given as delta is equal to x by square root of Re. So delta is inversely proportional to Re. So because the Reynolds number is such high, the boundary layer thickness is very small. This schematic is fundamental in boundary layer theory for explaining how real fluid flow around a flat plate differs from the ideal inviscid flow due to the existence and the effect of the boundary layer, which we feel in the real conditions. And that's it for question 15. Now we'll go to question 16. For flow at 10 meter per second past a thin plate, estimate the distances x from the leading edge at which the boundary layer thickness will be 2 mm or 5 centimeter for air, water at 20 degrees Celsius and 1 atmosphere. Oh, sorry. Just give me a minute actually. 5 mm. Okay, I'll just remove this question. For a flow for flow at 10 meter per second past a thin plate, estimate the distances x from the leading edge at which the boundary layer thickness will be 2 mm or 5 centimeter. 2 mm for or 5 mm. I'll come back to this question. For air, water at 20 degrees Celsius and 1 atmosphere. The at the below conditions, or else, because in each question the condition is differing, so I am just removing it. The distance as x from the leading edge at which the boundary layer thickness will be 2 mm for air is dash. So in the previous problem, what was done was, we were given a distance from the leading edge and we were asked to calculate the boundary layer thickness. Now in this question it is actually reverse. So we are going to do that. So first it is about flow at 10 meter per second past a thin plate and for air. Now the question is for air. So we'll take air properties. Density of air is 1.2 kg per meter cube. Viscosity of air is 1.8 into 10 power minus 5 kg by meter second. And velocity is equal to 10 meter per second. So flow of air and water at 20 degrees Celsius and 1 atmosphere, which was not given. So we are taking the conditions at 20 degrees Celsius and 1 atmosphere. So boundary layer thickness for air is 2 mm. So now we know the formula that Reynolds number is given by rho v x by mu. Now what is unknown here? Unknown is x. We know delta is equal to 5x by square root of rex. So if we can calculate it as x is equal to delta into square root of rex divided by 5. But one more problem is we don't know Reynolds number value. So we are first writing Reynolds number formula and then we are going in that. So delta is equal to 5x by square root of Rex. So delta x is equal to delta into square root of Rex divided by 5. So x square is equal to delta square into Rex. Okay, it should be Rex. And should I put it as x because it is confusing for delta and delta star. Sorry. And yeah. Oh, this x is confusing with that x. I put dot. Alright. So delta square into Rex divided by 25. So x square equal to delta square into rho v x by mu divided by 25. So this x and that x gets cancelled. So x is equal to delta square into rho v divided by mu divided by 25. So if we substitute in this formula, we will get the answer. So x is equal to delta square into rho v by mu. So delta is given as 2 mm. So did we write here? Yeah, 2 mm or 0.002 meters. So 0.002 square into 1.2 into 10 now. Velocity is 10 meter per second divided by 1.8 into 10 power minus 5. So that gives us 2.67 and divided by 25, that gives us 0.1067 meters. So the distance, the leading the distance x from leading edge at which the boundary layer thickness will be 2 mm for air is 0.1067 meters, or in other words it is 10.67 centimeters. So in the next question, the distance x from the leading edge at which the boundary layer thickness will be 5 mm for water is dash meters. So it is again now flow is water, so it is density of water, and it is 1000 kg per meter cube. So viscosity of water is 1 into 10 power minus 3 kg by meter second. And again flow velocity is same, velocity v is equal to 10 meter per second, and boundary layer thickness delta is equal to 5 mm. So again formula is the same, Reynolds number is equal to rho v x by mu, delta is equal to 5x by square root of Rex, or else we can write to find distance from the leading edge. Write it like this. Sorry. We can write it like this. Again, we'll take it to the next page. So Rex is equal to rho v x by mu, delta is equal to 5x by square root of Rex. So x is equal to delta into square root of Rex divided by 5. So now we are taking square on both sides. X square is equal to delta square by square Rex divided by 5 square is 25. So it becomes delta square into I'm just putting a dot so that delta and delta star doesn't get confused. So that's why. So rho v x by mu divided by 25, and it becomes x and x gets cancelled and it is delta square into rho v by mu. So x square and x gets cancelled divided by 25. So if we substitute it, what happens? We can remove this now. X is equal to 5 mm. It was given as delta boundary layer thickness is given as 5 mm, or in other words 0.005 meters. So 0.005 square into rho is 1000 into v is 10 into x is okay, x is not there, divided by mu is 10 power minus 3. It is 250 divided by 25, it is 10. So x is 10 meters. So 5 mm boundary layer thickness will be at a distance of 10 meters from the leading edge. This is for the case of water. Now moving on to question 18. The Reynolds number at a distance x corresponding to the previous question is dash. So what is asked? We are asked to find the Reynolds number at a distance of x corresponding to the previous question. So previous question it was water flow and x we found as 10 meters. So now we have to simply substitute it. So velocity is given as 10 meters and distance from the leading edge x is 10 meters, calculated in previous problem, question 17. Rex is equal to rho v x by mu. So rho is 1000, v is 10, x is 10 divided by mu is 10 power minus 3. So that gives us actually 10 power 8, because 10 power 5 in the numerator divided by 10 power minus 3 in the denominator, it gives us 10 power 8. So Reynolds number is 10 power 8. So now going to actually question 19. The distance x from the leading edge at which the boundary layer thickness will be 5 centimeter for air is dash meters. So we are asked to find now the boundary layer thickness is 5 centimeter and the flow condition is for air. So now we have to find this similar to the last problem only. So yeah, we'll put this in the next slide. So we'll have enough space. So given is again flow of air. So it is density of air. It is 1.2 kg by meter cube. And viscosity of air, it is 1.8 into 10 power minus 5 kg per meter second, and or Pascal second. Flow velocity is 10 meter per second, and boundary layer thickness is delta is equal to 5 centimeter or 0.05 meters. And Rex is equal to rho v x by mu, similar to what we did in the last problem. We are not doing anything new here actually. So Rex is equal to rho v x by mu. Delta is equal to 5x by Rex. So x is equal to delta into square root of Rex divided by 5. So we are taking square on all both the sides. So it becomes x square is equal to delta square into Rex divided by 25, or it is actually 5 square. So you can write it like this as well. Equal to delta square into rho v x by mu divided by 25. So delta square in xx gets cancelled. X is equal to, okay, x is equal to delta square into rho v by mu divided by 25. So now what is left, we have to just simply substitute it. So delta square, delta is 0.05 meters and delta square is 0.05 square into 1.2 into v is 10 into, okay, divided by 10 power minus 5, 1.8 into 10 power minus 5 divided by 25. So it is 66.67 meters. So distance x from a leading edge at which the boundary layer thickness will be 5 centimeter is 66.67 meters. So this is for air. Don't actually think logically of the numbers. It might not make sense because I just gave random numbers. Just a disclaimer, nothing else. So coming to the last question of today's session as well as for the whole session. A Reynolds number at distance x corresponding to the previous question is dash. So now we have to find the Reynolds number corresponding to the x in the previous problem. So flow velocity is actually 10 meter per second and distance from the leading edge is actually 66.67 meters per second, and also we need density of air. The previous problem was air, right? It is air and viscosity of air. We require both, and we'll write here. And formula is equal to Rex is equal to rho v x by mu. So rho is actually 1.2, v is 10, x is 66.67 divided by mu is 1.8 into 10 power 5. So it is actually 4, this number, in other words it is actually 2.44 into 10 power 1, 2, 3, 4, 5, 6, 7, 10 power 7. So Reynolds number is 4.44 into 10 power 7. If that is the case, what is this number actually? 4.4 crores roughly. Yeah, 4.4 crores, I think. It is 1000, 40,000, 4 lakhs. Yeah, 4.4 crores Reynolds number, or yeah, into 10, 4.44 into 10 power 7. So yeah, that's it for today's session. If you have any doubts, please ask. Or if you have any doubts from previous sessions also, we can discuss. We have time left. And yeah, all the very best for your exams. Just follow the guidelines for exams and instructions given, and it will be like yeah, prepare well and do the exam well, and I wish you all the very best. So yeah, if you have anything else to discuss, we can discuss now. Like from previous week's problem also, if you want, we can discuss. Okay. So yeah, since yeah, so yeah, I would like to thank you for attending this today's session as well as all the previous sessions, and we'll meet with some other course sometime in the future. But once again, I thank you for attending, and I wish you all the very best for whoever attended the exams, and whoever are attending the exams. So exams will be easy only. Like, just follow the guidelines provided in the website, and you'll be able to do it. And all the lecture videos and the lecture notes are made available to you. So make use of it if you want, whenever you want, actually. So that's it from my end. And yeah, I thank you for attending the sessions. And if there are any feedbacks, you can give it to me personally as well. And there will be uh, feedbacks taken from the NPTEL website as well. So you can submit it there also if you have any feedbacks. So yeah, that's it for from my end. Thank you. I'm closing the sessions. Thank you.